To achieve successful outcomes, it's crucial to align on business objectives rather than just focusing on tools. This means prioritizing faster lead times to production, minimizing incidents, and enabling safe, frequent deployments up to multiple times a day. Next, we need to define non-negotiable constraints, such as ensuring zero downtime deployments, instant rollbacks, and maintaining auditability and compliance with regulations like SOX, PCI, and GDPR. Setting measurable CI/CD targets is essential. For instance, we aim for a lead time of less than 1 hour from PR merge to production for most services, a change failure rate below 5%, and a mean time to recovery under 15 minutes. Additionally, we should ensure over 90% of changes are rolled out progressively, rather than in large batches. It's important to establish a deployment contract for each service, defining the flow from Git to CI, through artifacts to the environment, while using immutable builds and environment-specific configurations. We also need to clarify the ownership model, where the platform team manages the paved road, product teams handle pipelines and service-level objectives, and security enforces guardrails without acting as gatekeepers. Finally, we should commit to integrating AI-assisted workflows from the outset, leveraging features like test generation, pipeline configuration suggestions, and anomaly detection in build and deploy metrics. We've mapped our current workflow, which goes from development to pull requests, then manual QA, followed by change tickets and off-hours deployments. This process results in long lead times, brittle handoffs, and a lack of observability. Our failure modes heat map reveals that incidents from configuration and environment drift outnumber code bugs. When we need to roll back, it means redeploying an old artifact, which is slow and risks an unstable database state. Additionally, our monolith deployments are all or nothing, lacking control over blast radius. The data we gathered on lead times, mean time to recovery, and change fail rates helped identify bottlenecks like approval delays and flaky tests. We also found significant safety gaps, including the absence of canaries, feature flags, and automated production checks. Logs and metrics aren't tied to specific builds, making it difficult to correlate changes with their impact. Finally, our AI analysis of logs and incidents highlighted recurring patterns, showing that just 3 services were responsible for 70% of deployment-related issues, guiding our focus on where our CI/CD processes need to evolve first. The first layer focuses on trunk-based development combined with guardrailed pipelines. This means we maintain a single trunk with short-lived branches, ensuring that every change is quickly integrated. Mandatory pull request checks enforce quality through policy as code, such as Open Policy Agent, which governs tests, code coverage, security scans, and necessary approvals. This approach minimizes integration issues and enhances collaboration among developers. By establishing these guardrails, we create a consistent and reliable process that helps maintain code quality while allowing for rapid development. The goal is to ensure that every piece of code that enters the trunk is vetted, reducing the risk of introducing defects into the main codebase. A flag-first mindset is essential for managing risky changes. By shipping features behind a feature flag, we ensure that a rollout is simply a configuration change, not a redeployment of code. This minimizes risk and allows for quick adjustments. In a typical canary pipeline, we might start by directing 10% of traffic to the new feature, monitoring it for 30 minutes before increasing to 25%, then 50%, and finally 100%. At each stage, we automatically check key metrics like error rates, latency, and saturation. Our environment and cohort strategy begins with internal staff testing, then moves to beta users, followed by a regional rollout, and ultimately global deployment. This allows us to target specific user segments and control the impact of changes. To enforce safety, we implement guardrails that prevent direct jumps from 0 to 100% in the rollout process. Additionally, AI assists by monitoring canary metrics for anomalies, automatically pausing the rollout if it detects unusual patterns, and notifying the responsible team member. A single source of truth is crucial, and in our case, that's Git. We only promote immutable versioned artifacts, like Docker images and Helm charts between stages. When we need to roll back, we simply run a git revert and redeploy, avoiding any hotfixes directly in production. This keeps our deployments clean and predictable. Next, we use a 2-tier rollback model. The fast path allows us to quickly flip feature flags or adjust traffic weights, reverting to 100% of the old version in seconds. If a hard rollback is necessary, we redeploy the last stable build through our pipeline, ensuring consistency and reliability. We also have a rollback decision matrix. If we breach our service level objectives, we execute an immediate hard rollback. For error spikes, we take the fast path, pausing the rollout while we investigate. In cases of performance regressions, we may opt for a partial rollback. To ensure robust software delivery, we enforce a test pyramid in our pipeline. This starts with unit tests, progressing through contract tests, integration tests, and finally end-to-end tests, including non-functional tests like performance and load. The policy is clear. No manual production deployments are allowed unless all mandatory stages pass. Next, we utilize environment promotion as a quality gate. Code moves from pull request to ephemeral environments, then to staging canaries, and finally to production canaries, ensuring that only configuration changes occur while maintaining the same artifacts and infrastructure as code. We also leverage AI in our validation loop. A large language model generates tests based on production incidents and specifications, while anomaly models evaluate logs, metrics, and traces against historical baselines. Before a full rollout, we conduct automated canary analysis, comparing error rates, latency, and key business KPIs between the canary and control groups. If any service level objective or business guardrail is breached, the system automatically halts and triggers a rollback. Finally, we provide fast feedback to developers through pipeline comments on pull requests, detailing failed tests and suspected root causes. We also quarantine flaky tests and automate ticketing to ensure that noise doesn't impede safe delivery. To effectively measure success, start by defining a concise set of KPIs for each service, focusing on DORA metrics like lead time, deployment frequency, mean time to recovery, and change failure rate, alongside SLOs such as latency, error rate, and saturation. This ensures that every metric is actionable. Next, integrate these metrics into your rollout process using canary deployments and feature flags. If the error rate in the canary exceeds a set threshold, or if the 95th percentile latency surpasses a baseline plus a margin, the system should automatically halt or roll back the deployment. This creates a feedback loop. From committing code to continuous integration and deployment, telemetry captures logs, metrics, and traces. AI can analyze this data for anomaly detection during post-deployment windows, helping identify subtle regressions quickly. Finally, to foster a culture of continuous improvement, ensure that every incident or noisy alert results in the creation of a new pipeline rule or test, such as an SLO guardrail or canary check. To achieve scalability and future-proofing in our CI/CD processes, we start with a modular pipeline graph instead of a linear script. This means we treat our CI/CD as composable stages, like build, test, verify, deploy, and observe, connected through templates. When new technologies emerge, like WebAssembly or different testing stacks, we can simply add a module instead of rewriting the entire pipeline. Next, we implement an environment-agnostic deploy layer. This involves a standard contract consisting of an artifact, configuration, and rollout policy that works across various orchestrators and clouds. This flexibility allows us to swap out orchestrators without altering our application pipelines. We also define policy and guardrails as code. By embedding organization-wide rules into a versioned policy repository, any changes in compliance can be updated once and inherited by all pipelines, ensuring consistency. Additionally, we create pluggable AI and automation hooks. These reserved hooks, like post-test and pre-prod, allow us to integrate AI analyzers for tasks such as log anomaly detection and risk scoring. As AI technology evolves, we can upgrade these hooks without changing the overall pipeline structure. For execution, we utilize multi-tenant, horizontally scalable runners. These stateless executors can auto-scale and manage per-team queues, allowing us to offload heavy tasks to shared services. This setup maintains high throughput as teams and repositories grow, eliminating the need for constant tuning. Lastly, we establish versioned pipeline contracts, such as Pipeline V1 and V2, with defined deprecation windows. This approach enables large-scale evolution, allowing services to opt in to changes when they are ready, facilitating gradual transitions, like moving from canary releases to a progressive delivery platform. To enhance security integration, we start by shifting left in our pipeline. This means implementing mandatory checks like static application security testing, dependency scans, and infrastructure as code scans right from the pull request stage. This proactive approach ensures vulnerabilities are caught early. We also enforce security policies as code, using tools like OPA or Sentinel to gate merges and deployments, ensuring compliance before any changes go live. Next, we focus on signed, traceable artifacts. By linking source commits to a software bill of materials and implementing image signing with tools like Sigstore or Cosign, we ensure that every artifact is verifiable. At deployment, we enforce signature and provenance checks to maintain integrity. We establish environment guardrails by assigning least privileged deploy identities for each environment: development, staging, and production. Additionally, we implement network policies and ensure secrets are retrieved from a vault, avoiding inline secrets in CI to minimize exposure. For runtime and rollout security, we introduce hooks that block canary and feature flag deployments if new CVEs or policy violations are detected. We also utilize web application firewalls, runtime application self-protection, and runtime scanners to automatically tighten rules against suspicious traffic. Lastly, we create a continuous security feedback loop. This includes AI-assisted triage of vulnerability findings, prioritizing them based on exploitability and potential impact. We track security metrics like mean time to recovery for vulnerabilities, the percentage of signed artifacts, and policy violations on our continuous delivery dashboards. To enable AI effectively, we first integrate it into our observability firehose, which combines logs, traces, metrics, and feature flag events. This data is streamed to an anomaly detection engine like Datadog Watchdog or a custom solution, allowing us to identify issues proactively. Next, we implement predictive risk scoring before a full rollout. By analyzing change metadata, such as the files affected and past incidents, we can tag builds as low, medium, or high risk, which informs how aggressively we can deploy canaries. For real-time monitoring, we compare a baseline from the past week against current canary metrics. If we detect significant deviations, like a high Z-score or changes in user behavior, we can automatically freeze the rollout and trigger a rollback. This leads us to a simple mental model. We deploy, run a canary at 5%, check AI scores and service level objectives. Depending on the results, we either proceed with more extensive deployment, hold for human review, or roll back if necessary. Finally, we create a feedback loop where post-incident data and rollout outcomes continuously retrain our models, enhancing our ability to catch problematic releases while ensuring safe ones continue smoothly.